Imagine you're monitoring a 500-dimensional stream of financial sensor data, right? And suddenly, the underlying market dynamics just shift.
Yeah, a complete regime change.
Exactly. And to mathematically pinpoint that exact microsecond using standard convex optimization, you would have to construct and solve a quadratic program so massive it would just, likely freeze a standard computing cluster.
Oh, absolutely. It's totally intractable.
Right. So the typical response in our field is to just accept a heuristic approximation, right? You trade away mathematical certainty, you just kind of hope the solver gets close enough to the global optimum. But what if the secret to solving that massive optimization bottleneck wasn't just, throwing more GPUs at it? What if it was actually deploying a mathematical trick derived from 1960s Apollo-era control theory?
And that specific cross-pollination of disciplines, that's really the central focus of what we are deep diving into today, because it's fascinating.
It really is.
We're breaking down a 2017 NIPS paper. It's titled An Efficient ADMM Algorithm for Structural Break Detection in Multivariate Time Series. And this is authored by Alex Tank, Emily B. Fox, and Ali Shojaie from the University of Washington.
The mission for this deep dive, for those of you listening who deal with these kinds of optimization headaches, is to really deconstruct the exact mechanism these authors use to bypass those limitations of approximate solvers. They took this massive, unyielding, penalized least squares problem, decoupled it using the alternating direction method of multipliers ADMM, and then recognized that the resulting subproblem was actually it was a classical Kalman smoothing task in disguise.
Right. And for an audience steeped in the mathematics of machine learning and data science, analyzing this paper is basically a masterclass. It's an exercise in understanding how an intractable bottleneck in one specific domain can map perfectly onto a highly optimized dynamical system from a completely different era.
Yeah, exactly.
Yeah.
So to map that translation accurately, we first need to establish the foundational architecture of the model itself.
Right, let's set the stage. So the authors define the underlying generative process of the multivariate time series. We'll denote that as X sub t, as a structural break vector autoregressive model, or a VAR model.
Okay, so we're dealing with a p-dimensional series with a lag order of k.
Yes. And the defining constraint of this whole system is that there are an unknown number of breakpoints, let's call that L. The core assumption here is that the time series remains completely stationary between these breaks.
Okay, meaning the underlying autoregressive parameters only shift at those specific unknown intervals.
Exactly. So the objective is to estimate both the number of those structural breaks and their precise locations, alongside the autoregressive transition matrices for each of those stationary segments.
Right, and the formulation for estimating those parameters relies on a penalized least squares approach, right?
It does. They introduce local autoregressive parameters, A sub t, which represent the transition matrix at every single time step t.
But wait, if you leave that unpenalized, fitting a separate matrix for every time step would obviously lead to extreme overfitting.
Oh, completely. You'd just be fitting noise.
Yeah.
So to force the structural break assumption onto the model, the idea that the series is mostly stationary, they introduce a fused group lasso penalty to the objective function.
Okay, let's unpack that penalty.
Okay.
Specifically, they penalize the objective with lambda times the sum of the Frobenius norm of the difference between consecutive parameters. So the sum of the Frobenius norm of A sub t minus A sub t plus 1.
That's the one.
Which is essentially, and I love this analogy, it's like applying total variation denoising directly to the weights of the autoregressive model rather than the observed data itself. We are actively penalizing the derivative of the model's parameters across the temporal dimension.
That is a great way to think about it. The only time the difference between consecutive transition matrices isn't driven entirely to zero is when the data strongly dictates a massive structural break.
Because the Frobenius norm is operating as the group lasso penalty here.
Right. Because it applies to the entire matrix of differences across all elements simultaneously, it basically enforces piecewise constancy across the transition matrices.
And the hyperparameter lambda dictates the sparsity of those structural breaks, right? A larger lambda imposes a harsher penalty on any change, resulting in fewer estimated breakpoints.
Exactly. Formulating the structural break problem as a convex objective, this is mathematically elegant, but executing it introduces a really severe computational roadblock.
Yeah, because looking at the landscape of methodologies prior to this paper, finding the true global optimum for this specific convex formulation was, well, it was computationally prohibitive at scale.
Yeah, the alternative methodologies all carried really significant compromises. I mean, if you step outside convex optimization entirely and look at Bayesian approaches, you see models relying on switching Markov processes to dictate the transitions between regimes.
And the fundamental issue there is the reliance on Markov chain Monte Carlo methods.
Precisely. Because MCMC has to explore this huge combinatorial space of potential partition points. As the length of the time series n grows, the state space of possible segmentations just explodes.
It makes it practically intractable for high-dimensional or long series.
Right. And similarly, if you look at non-parametric approaches analyzing spectral density jumps, they just lacked the parametric structure required to easily interpret the changing transition dynamics.
So if you remained within the convex optimization space, attempting to solve the fused group lasso penalty directly, what did people actually do?
Well, the standard practice was to rely on approximate algorithms. Approximate group least angle regression, or group Rs, was kind of the primary tool.
But the critical flaw in relying on group LARs for this application is that it inherently lacks guarantees for returning the true optimal solution, doesn't it?
Exactly. It is purely an iterative approximation. So the authors of this paper chose to abandon the heuristic approach entirely. They wanted an exact solver.
And they pursued that by utilizing the alternating direction method of multipliers.
Right, ADMM. Setting up the ADMM framework requires a structural reframing of the objective. They execute a change of variables, defining a new parameter, theta sub t, which is equal to the difference, a sub t minus a sub t plus 1, for time steps greater than 1.
Okay, so this parameterization maps the objective into a standard group lasso regression format. You're basically minimizing the squared Frobenius norm of the prediction residual, plus lambda times the sum of the Frobenius norms of theta sub t.
You've got it.
But I have a direct pushback here. Even with that parameterization, the core bottleneck remains, right? The smooth least squares term is highly coupled with a non-smooth group lasso penalty on theta sub t. ADMM is the standard playbook for decoupling loss from non-smooth regularization, but by splitting it, don't we still end up with a global theta update that is a massive, highly coupled quadratic program?
You're jumping right to the hard part.
I mean, for a p-dimensional series over n time steps with lag k, the theta vector contains p squared times k times n variables. A naive quadratic solver would require an operation scaling cubically with the length of the time series. How is that actually more efficient?
It's not. That massive computational cost is precisely why approximate solvers were previously favored. The innovation of this paper lies entirely in how they handle that specific global theta update.
Okay, so what's the trick?
They bypass the naive quadratic programming approach by first proving that the global update can be cleanly decomposed. Because the objective function is separable across the rows of the transition matrices, the massive program actually breaks down into p completely independent optimization problems.
Oh, wow. Okay, that immediately allows for parallelization, basically reducing the dimension of each subproblem by a factor of p.
Exactly. You solve one independent problem for each row of the time-dependent autoregressive parameters.
But parallelization just provides a speed up. It doesn't solve the core cubic scaling issue.
Right. The true breakthrough requires looking at the algebraic structure of the subproblem for a single row. The authors recognize that the resulting optimization problem perfectly mirrors, and I mean perfectly, the negative log likelihood of a classical Gaussian state space model.
Wait, really? I want to break down exactly why that mathematical mapping works. Because for you listening, this represents the conceptual core of the entire paper. In convex optimization, when you apply an L2 penalty to the difference between a parameter and a target value, the resulting term takes the form of a squared Euclidean distance.
Correct.
But in probability theory, if you take the natural logarithm of a Gaussian probability density function, the exponential term drops down, leaving you with
a squared Euclidean distance. The algebraic structures are absolutely identical.
That is so elegant.
Isn't it? To decouple the variables, ADMN introduces an auxiliary parameter, W sub t, and imposes the strict equality constraint that W sub t must equal theta sub t.
Right, which allows the formulation of the augmented Lagrangian.
Yes. The objective function expands to include the least squares loss, the sparsity penalty on W sub t, and the augmentation terms that bind W sub t and theta sub t together. You have a penalty parameter, rho, scaling the squared Frobenius norm of the difference between the theta sub t and W sub t.
And you also introduce the Lagrange multipliers, omega sub t, interacting with that difference via a trace operator.
Exactly. So going back to the subproblem, it is asking the solver to minimize a squared error term related to the observations, plus a squared penalty term keeping the parameters theta close to the auxiliary variable w.
So by reversing the logarithm, you can interpret the subproblem as maximizing the likelihood of a dynamical system where a latent state evolves over time and generates noisy observations.
That's the exact mapping.
Okay, if we map the variables directly, the latent state in this constructed dynamical system corresponds to the autoregressive parameters for a single row. The state evolution equation defines how those parameters shift from one time step to the next.
Yes. And in a standard state space model, the state a sub t equals the previous state, a sub t minus 1, plus some deterministic bias, plus Gaussian process noise.
And in this ADMM subproblem, that deterministic bias, which we can call mu sub t, is derived directly from the ADMM auxiliary variables, right?
Yes. The required update step isolates the bias as the difference between the w variable and the Lagrange multiplier. So mu sub t just equals w sub t minus omega sub t.
So if we follow the mapping logic, the process noise variance in our state space model must correspond to the augmented Lagrangian penalty parameter. Since the ADMM formulation penalizes the squared difference scaled by rho, the mathematical equivalent in the Gaussian likelihood is a covariance matrix defined by the inverse of that penalty.
You nailed it. The state evolution noise is distributed as a Gaussian with mean 0 and a covariance of 1 over rho times the identity matrix. Finally, the observation equation in our mapped state space model simply states that the observed data point equals the lagged data transposed times our latent state plus Gaussian observation noise.
So by recognizing that an L2 penalty inside an ADMM iteration perfectly maps to the negative log likelihood of a Gaussian distribution, the authors eliminated the need for a bespoke convex optimization solver entirely for the theta update.
Entirely. If the optimization objective is equivalent to a state space log likelihood, then finding the optimal theta parameters is mathematically identical to finding the maximum likelihood state sequence for that dynamical system.
Which is a problem that control theory solved decades ago.
Exactly. Because the constructed state space model is purely Gaussian, the mean of the posterior distribution is strictly equal to the mode. Finding the expected value of the latent sequence given the observations mathematically guarantees you have found the exact global optimum for the theta update in the ADM iteration.
And to compute that expected value, they deploy the Rauchtan-Streibel smoother, right? The RTS algorithm.
That's the one. It's foundational for estimating latent states in linear dynamical systems, and it operates through two distinct passes over the time series.
Right. The first pass is the forward Kalman filter. Starting at t equals 1, it recursively computes the filtered state estimates and their predicted covariance matrices moving forward in time. At each step, it calculates the Kalman gain, which, determines how much the internal state estimate should be updated based on the residual of the new observation.
And once the forward pass processes the entire series up to time n, the algorithm initiates the backward smoothing pass. It starts at the final time step and moves backward, computing smoothed state estimates.
So this pass incorporates future information to refine the past state estimates. It calculates a smoothing gain matrix, often denoted as C sub t, which relies on the filtered covariance from the current step and the inverse of the predicted covariance from the next step.
And the efficiency gained here is profound. Both the forward filtering and backward smoothing passes require a constant number of matrix operations at each individual time step.
Meaning there is no operation that scales exponentially or cubically with the temporal length?
Exactly. The computational complexity for completing the entire theta update, finding the exact global optimum for that ADMM step, is strictly O of n.
O of n. A heavily coupled quadratic program with p squared kn variables is solved in linear time. That fundamentally outperforms any attempt at direct optimization. But wait, the ADM framework still requires alternating to the W update. So while the theta variable goes through this whole elaborate Kalman smoothing journey to handle the time series dynamics, the W variable is basically just acting as our bouncer, applying a straightforward soft thresholding to enforce the sparsity of the structural breaks.
That's a really good way to phrase it. Because of the explicit decoupling achieved by the augmented Lagrangian, the W update isolates the group lasso penalty. The closed-form solution for updating W in this context is the proximal operator for the fused group lasso,
which manifests as a block soft thresholding step. Instead of zeroing out parameters blindly, the soft thresholding proximal operator acts like a mathematical friction coefficient. It evaluates the Frobenius norm of the current theta estimate plus the Lagrange multiplier. If that combined magnitude is below a strict threshold dictated by lambda over rho, the friction overcomes the signal, and W is driven exactly to 0.
And if the magnitude exceeds that threshold, the variable escapes being zeroed out, but its value is still shrunk towards 0 by a constant scaling factor. That continuous shrinkage is really what defines soft thresholding compared to hard thresholding.
The architectural beauty of the algorithm is how these two disparate mechanisms iterate. The RTS smoother processes the data temporally, proposing smooth transitions across the autoregressive parameters. The soft thresholding proximal operator then processes those proposes spatially, applying massive friction to any change. Only when the temporal data strongly indicates a regime shift does the magnitude overcome the friction, locking in a non-zero structural break.
The theoretical synthesis of these mechanisms is brilliant. It provides an exact O of n solver, but evaluating its viability requires looking at the empirical results and, acknowledging the specific computational constraints. The authors tested the algorithm using simulated multivariate time series to verify the exactness of the solver.
Let's talk about those simulations. The primary one involved a 10-dimensional series, so p equals 10, with n equals 300 observations. They generated the data with 2 explicit structural breakpoints, resulting in 3 distinct stationary regions, each governed by different underlying autoregressive processes.
Right. And in terms of hyperparameter tuning, they defined a breakpoint detection event as any time the Frobenius norm of the parameter change theta sub t exceeded a strict numerical tolerance of 0.005.
And running the ADMM algorithm across different penalty scales, they found that a setting of lambda equals 5 allowed the algorithm to perfectly identify the exact locations of the structural breaks.
Perfect identification. The empirical validation confirms the exact solver works flawlessly.
However, we have to analyze where the computational debt was actually shifted. The algorithm successfully achieves O of n scaling for the temporal dimension, meaning analyzing a series of 10,000 time steps is computationally trivial. But analyzing the mathematics of the RTS smoother reveals a severe vulnerability regarding the spatial dimension p and the lag order k.
Yeah, the spatial complexity is the hard bottleneck for this approach. The source of that bottleneck lies specifically within the backward smoothing pass of the RTS algorithm.
Right. When calculating the smoothing gain matrix C sub t at every single recursive step backward, the algorithm must compute the inverse of the predicted covariance matrix from the forward pass. And the dimensionality of that covariance matrix is p times k by p times k.
And as we know, inverting a matrix inherently scales cubically with its dimension. Therefore, at every single time step, the algorithm is forced to execute a matrix inversion that requires O of pk cubed operations.
So for the simulation where p equals 10 and k equals 1, the covariance matrix is 10 by 10. Executing a cubic inversion on a 10 by 10 matrix 300 times during the backward pass is barely a blip on a modern CPU. But if we scale the problem to the 500-dimensional financial sensor data stream we discussed at the start of the deep dive,
that covariance matrix becomes 500 by 500.
Yeah. Inverting a 500 by 500 matrix at every single time step rapidly devolves into a computational nightmare. The temporal complexity remains linear, but the feature dimension complexity just explodes.
And to be fair, the authors openly acknowledge this mathematical reality in their discussion. The standard RTS smoother solves the temporal problem perfectly, but to apply this ADMM framework to truly high-dimensional applications, future work will have to integrate alternative Gaussian state space smoothers that can estimate the expected latent state without relying on exact, dense matrix inversions.
It's the critical constraint you practically must account for. You gained an uncompromised exact linear time solver that guarantees the global optimum, provided your spatial dimensions and lag orders remain within a manageable threshold.
Right. So summarizing the contribution of Tank, Fox, and Shojaie, they recognized a persistent flaw in how machine learning approaches structural break detection in multivariate time series. The reliance on approximate convex solvers like group LARs provided computational feasibility, but at the cost of theoretical guarantees.
And their solution was to fundamentally rewire the optimization pipeline. They decoupled the fused group lasso objective using ADMM, isolated the massive, highly coupled global update, and proved that it could be solved exactly by mapping it to the negative log likelihood of a classical Gaussian dynamical system.
The synthesis of context optimization principles with classical control theory algorithms, like the Rashtung-Streibel smoother, is really an exceptional example of recognizing underlying mathematical symmetries to bypass modern computational limitations.
It's incredible work, and it leaves us with a highly provocative thought regarding the current trajectory of algorithmic development for everyone listening. If an intractable convex optimization bottleneck can be dismantled and solved optimally in linear time, simply by recognizing its algebraic equivalence to a 1960s state space model, what other highly complex, compute-heavy regularization bottlenecks currently bogging down modern deep learning architectures are secretly harboring exact linear time solutions?
Just waiting for someone to map them back to classical dynamical systems theory.
Exactly. Something for all of you to interrogate the next time you're staring at a seemingly intractable quadratic program. Until next time.